Hi everyone, this is the continuation of third module. So that is today is about types of flow, critical flow, subcritical flow and supercritical flow in the non-uniform flow concept. That is the first one. Critical flow, it is defined as the flow at which the specific energy is minimum or the flow is considered corresponding to the critical depth. So the critical flow will be represented in terms of Froude number. We know Froude number, it is the ratio of inertia force by the gravitational force. But what is the critical flow? If you are identifying the flow is critical, then the Froude number value is equal to 1. When it is coming to the subcritical flow or streaming flow, when the depth of flow in which the channel is greater than the critical depth, or you can say the subcritical flow or the streaming flow, as well we can define in terms of Froude number. So when the value of Froude number is less than 1, we'll say that will be a subcritical flow. And supercritical flow, when the depth of flow in the channel is less than the critical depth, the flow is said to be supercritical flow or shooting flow. For this type of flow, the Froude number value is greater than 1, we'll say that will be a supercritical flow. So we can define critical, subcritical and supercritical flow with respect to Froude number. If you are saying the Froude number value is 1, that is critical flow. If the Froude number value is less than 1, subcritical flow. If the Froude number value is greater than 1, supercritical flow. Then move on to the alternate depths. So alternate depths is very much essential while doing the hydraulic jump derivation. But before that, we should know what exactly the alternate depth. In the specific energy curve, as shown in the figure, what we had discussed the previous one, specific energy and specific energy concept. So in that, the specific energy curve, the point C corresponding to the minimum specific energy and the depth at point C is critical depth. So we can identify that where we'll be having the specific energy is minimum, we'll say that will be as critical depth. If the depth is critical, we'll say that will be as critical velocity. So these are the two depths, one greater than the critical depth, the other one is smaller than the critical depth. These two depths for a given specific energy are called as alternative depths. So their depths are shown as H1 and H2 in the figure. So condition for maximum discharge for a given value of specific energy. So now here we have a condition to find out the maximum discharge with respect to the value of specific energy. So we know that specific energy will be represented as capital letter E, and that will be represented by H plus V square by 2G. So V is the velocity that will be calculated by discharge by area, that is Q by A, that is Q by area is B into H. Then E is equal to H plus Q square by B square into H square. So we know that H plus V square by 2G. So V square can be replaced as Q square by B square into H square into 1 by 2G. Now E will become H plus Q square by 2GB square into H square. Then if you want to represent in terms of Q square, then we can do cross multiplication. Then the equation will become E minus H into 2 into G into B square into H square will be equal to Q square. Or you can write Q is equal to square root of E minus H into 2G into B square into H square. You can take B will be outside, then Q is equal to B into square root of 2G into EH square minus H cube. For maximum discharge, the term EH square minus H cube, we have to be considered with respect to the depth of flow. So now the specific energy is with a depth of flow, that is EH square minus H cube should be maximum. So that will be considered. We have to differentiate the specific what you are getting the discharge. For maximum discharge, Q is equal to B into square root of 2G into AH square minus H cube. Then we have to differentiate EH square minus H cube with respect to the depth of flow. Then if you differentiate that, we'll get E is constant, 2EH minus 3H square is equal to 0, or 2E is equal to 3H. Then E will be equal to 3 by 2 H, or we can say 1.5 times of H. So H is nothing but HC. So we have to know from the previous one also, where H will become HC, then E will become E minimum. So E minimum is equal to 1.5 times of HC. So that already we know that. As well, if it is another condition for maximum discharge, again the specific energy will be equal to 1.5 times of depth. Here in the equation, specific energy is equal to 1.5 times of depth of flow. Thus equation 1 represents the minimum specific energy and H is critical depth. Hence the condition for maximum discharge for a given value of specific energy is that the depth of flow should be critical. The numericals, the specific energy for a 3 meter wide channel is to be 3 kg meter per kg. What would be the maximum possible discharge? So what we have discussed with the previous condition of E is equal to 1.5 times of Hc. Here they are saying that there will be of maximum discharge. Then what will be the specific energy? And we can see here 3 kg meter per kg. Kg get cancelled, and again you'll get the specific energy is meter itself. So to make it confused, they may express in terms of kg meter per kg, or they can say Newton meter per Newton. So the width is 3 meter and specific energy is 3 meter. For the given value of specific energy, the discharge will be maximum only when the depth of is critical. Hence, for maximum discharge, H will become Hc. That is, E is equal to 3 by 2 times of Hc, or Hc will be equal to 2 by 3 times of E. Then we have to find out what is Hc. That is, Hc is equal to 2 by 3 into 3. So you'll get 2 meter. The critical depth is 2 meter. Then we have to substitute in the maximum discharge equation, that is A into V. Q max is equal to area into velocity. Area is B into H, that is H will become Hc. So B into Hc into Vc. Then we have B into Hc, but Vc is unknown. At critical depth, the velocity will be critical. So Vc is equal to square root of G into Hc. That is 9.81 into 2. And then we'll get Vc will be equal to 4.429 meter per second. Then we have to substitute Q max is equal to B into Hc into Vc, that is 3 into 2 into 4.429. Then we'll get Q maximum is 26.57 meter cube per second. Then we'll move on to the 8th numerical. The specific energy, we can see that in the previous session of video, we have discussed 6 numericals on specific energy concept, that is with respect to critical depth, critical velocity, as well as for minimum specific energy. Now we have 7th and 8th numerical, it is on specific energy for maximum discharge condition. Okay, so 8th numerical, the specific energy for a given 5 meter wide channel is to be 4 Newton meter per Newton. I said you the previous one also, the specific energy can be expressed in terms of kg meter per kg, or it may be of Newton meter per Newton. So again Newton will get cancelled. Then the remaining specific energy is 4 meter. If the rate of flow of water through the channel is 20 meter cube per second, determine the alternative depths. So here they ask you to find out the alternative depths of the flow. So we have to write the given data. B is equal to 5 meter and E is equal to 4 meter and discharge is 20 meter cube per second. And we have the condition for specific energy. E is equal to H plus V square by 2G. And V, we know that it is Q by A. A is B into H. So Q by B into H, that is 20 by 5 into H. So we can just substitute specific energy as H plus V square by 2G. So V square by 2G as V square as 4 by H. So 4 by H whole square into 1 by 2G. Then we'll get here, 4 square is 16. So 16 by 2 is 8. So I'll get H plus 8 by G into H square. Again, that you'll get as, specific energy is given as 4. So 4 is equal to H plus 8 by GH square. Then you'll get that will be as H plus G is 9.81. So 0.8155 by H square. You can just do cross multiplication taking the factors. So 4H square is equal to, just do that, H square on both the sides, multiply H square on both the sides. So 4H square is equal to H cube plus 0.8155. H square will get cancelled. Then H cube minus 4H square plus 0.8155 is equal to 0. So now we have the equation. By solving, we have to solve two unknowns, that is H cube, H square and power 0. So we can just see that for H cube minus 4H square plus 0.8155. So by applying two unknowns, we can find out H1 and H2, that is the alternative depths. So H1 is 0.48 meters and H2 is 3.93 meters. So these are all the alternative values of H. One is H2, other one is H1. So these are all the numericals which is related to alternative depths and the maximum of specific energy condition, as well as with respect to the types of flow. In the next numerical, we can discuss in the next part. We can go on to the hydraulic jump part. After the deriving the hydraulic jump, then we move on to the hydraulic jump numericals. That may complete the module 3. So in the next session, I'll just go through with the hydraulic jump concept. all of you, before going to this video, just see the notes. After seeing the notes, then you can go through the video, then it will be helpful. Thank you.